Let's talk about continuous random variables in relation to how they differ from discrete random variables. Let's first remind ourselves that a random variable, in general, is defined with a capital letter, and its individual realizations are represented with the lowercase version of that letter. For example, discrete random variable capital Y is defined to count the number of heads that appear in a single coin flip, and little y could take on the realization 0 or 1, as either 0 head or 1 head will result from a single coin flip. And we can find the probability that y takes on the value 0 and the probability that y takes on the value 1. We said that a discrete random variable has a probability distribution P of y, which I refer to as the probability that capital Y is equal to little y, as I think that notation is more descriptive. The probability distribution enumerates the possibilities for each realization and the probability of each realization. We can depict it graphically with a bar graph, where the horizontal axis displays the realizations of the random variable, and the vertical axis displays the probability. This is also referred to as a probability mass function. A continuous random variable, on the other hand, has a probability density function, f of y. I also refer to this as a probability distribution function as well, as is common. Also common is the abbreviation PDF. We only use the term PDF to describe the function f of y, and this is only for a continuous random variable. The function f of y gives us an idea of the shape of the distribution of the continuous random variable. Is it symmetric? Does it have a long tail in one direction or another? Is the left-hand side truncated at 0? But on its own, f of y doesn't tell us much about the probability of a range of realizations. We have to find the area under the curve between the two values to calculate the probability of the range of those two values. That's the biggest difference in visualizing discrete and continuous random variables. For a discrete random variable, we read the probability of the realization from the vertical axis, while for a continuous random variable, we have to find the area under the curve between two values. Again, f of y doesn't help us with the probability directly. How do we find the area under the curve between 2 points? Yes, with an integral. To find the probability that the continuous random variable y takes on a value between 2 points a and b, we integrate f of y and evaluate between a and b. The same properties of probability hold for continuous distributions. The area under the curve f of y between points a and b must be between 0 and 1, inclusive of 0 and 1. That is, the probability that y lies between a and b must be between 0 and 1. And the probabilities of all mutually exclusive intervals of y must sum to 1. That is, the integral of f of y evaluated from the distribution's lower bound to its upper bound must be 1. You probably noticed that when I've been talking about the probability of a continuous random variable, I always measured it for a range of values. That is, what's the probability that y is between a and b? That's because the probability of an individual realization of a continuous random variable is 0. From a practical perspective, this makes sense. There are an infinite number of realizations on a continuous number line, so the probability of any particular value must be 0. There are way too many possibilities for any one realization to actually have a probability. And from a mathematical perspective, we calculate the probability of a range of realizations under f of y between two values. So naturally, there's no area under the curve for a single point. Therefore, the probability of a single realization of a continuous random variable must be 0. That has implications for how we write the probability of a range. As the probability of a particular value is 0, we can write the probability of a range with either equalities or strict inequalities. And the outcome is the same. We still integrate f of y between a and b. Also recall from our discussion of discrete random variables that the cumulative distribution might be helpful. That was the probability distribution that accumulated probabilities on the vertical axis, describing the probability that y is less than or equal to some value y0. For example, with counts, the lower bound is often 0, so we accumulate the probability of realizations of y from 0 up to the value that we're interested in. In our example on the screen, we see the cumulative probability of 2 is 0.86. That is, the probability that the random variable takes on a value of 2 or less is 0.86. We have the same idea with a continuous random variable. The cumulative distribution function, or CDF, is referred to with a capital F. That is, capital F of y is the cumulative probability from the lower bound of the distribution up to value y. This is found as the integral of f of y evaluated from the lower bound up to y. The cumulative distribution function is usually a smooth curve, especially relative to the discrete random variable. The expected value of a continuous random variable is similar in concept to what we saw with the discrete distribution. The expected value of y for a discrete distribution was the realization of the random variable multiplied by the probability that that realization occurs, summed across all realizations. As continuous random variables are measured on a continuous number line, we don't use summations, we use integrals. That is, the expected value of y is the integral of y times f of y evaluated between the lower bound and the upper bound of the distribution. Recall that the variance is the expected value of y squared minus the expected value of y quantity squared. To find the expected value of y squared, we integrate y squared times f of y and evaluate between the bounds. Some distributions have different limits. Some range from negative infinity to positive infinity, some range from 0 to positive infinity, and some are truncated by two values. And each of those distributions is used to describe different phenomena. We're speaking generally in this video, so we're light on example problems. We'll see some common distribution functions, those f of y, for different continuous random variables and work out some problems for those specific distributions.